So we are going to continue where we left yesterday. So in this class we are going to start with something called transformations, orthogonal transformations in the context of how we study linear transformations and also in a sort of unitary transformations. So since the previous section was maybe more or less related with unitary transformations, but orthogonal transformations, if I use the words, so orthogonal transformations on real inner product space need not have proper values. So the other unitary transformations we might do had proper values, but these need not have proper values. So the spectral theorem, which we just it gives us information about the orthogonal transformations. So the theory of complexifications, which was invoked to so it was the point is that if we suppose, for example, leave away this thing. So if we suppose that U is an orthogonal transformation, then on a finite dimensional vector space, so product space, and on a transformation on a finite dimensional vector space V, and U plus be its extension in terms of complexifications. So the point is that why we complexified a given finite dimensional vector space was that it had some advantages of just making that inner product positively definite. That was the advantage. So, but now if we construct orthogonal spaces, which don't necessarily that they have proper values, so how can that procedure of complexification be introduced in this context? So, if U is an orthogonal transformation, and U is a complexification, which would denote as this, and U star or U, this is this thing, this is the property on U, then U star, so this is complexified this thing, so this will also be 1. This means this is on V plus, this means U plus is unitary. Now what we are going to do is, if lambda is we define lambda as like this, where alpha and beta are real, and M be a subspace consisting of solutions U plus Z is equal to lambda Z in V plus. And if lambda is not the proper value, so proper value of u plus, then so it will be 0, because it's orthogonal transformation. So if it is that way, but if z is in M, and if we write z as x plus iota y, x plus iota y, then with x and y in V a vector space, then what will happen? Then how should we define this here? So ux plus iota vy, this is one vector space, another vector space, u is orthogonal transformation to. So if these two vector spaces u and v, so we can write it ux plus iota, sorry, u, if you complexify it, if you complexify this transformation, you can write it in, we write it in terms of x plus iota y and x minus iota y, alpha plus iota b, and uy can be written as x plus iota y. So you can have identification of reals with real and complexes with complex. So if you just simplify it, so you can say ux can be written as alpha x minus beta y, and uy can be written as beta x plus alpha y. So if you do one thing, you multiply this equation 2, multiply equation 2, I have 1 and 2, by iota and subtracting first from the second, second from the first, you will have ux minus iota ey, ux minus iota uy is equal to, you can, if you simplify it, this is iota, and you simplify the 2, you can write it as alpha minus iota beta into x minus iota y. So this means what? This means that u plus z minus is equal to lambda bar z bar. The z bar, you can write it as a complex conjugate ux minus iota vy. So this is the solution of it in the right hand side. And z is a sort of a convenient symbol. It can be alpha plus iota beta or x minus iota, x plus iota y. So you can say, but since it's a complex conjugate, you can say u plus z has solution lambda z. This is one of the solutions, or this is uz. So, or if you take u plus this one, it will have. But here, if it is z, it will be z bar, or complex conjugate of it will be lambda bar z bar. So it is reversible in the sense that mapping from z to z bar, map complex plane, a conjugate of the complex this thing. So this means if lambda is the one of the values, lambda bar can be one of the conjugate values which is associated with it. So the coefficients of this characteristic polynomial are real. That's it. Now, if what we have said that if the complex conjugate values, so if it's so we have started that the proper values. So if the proper values do not have proper values, maybe then it's is zero. Then the this determinant, this a into b, it will come out to be zero. So if it's this that way, how can we just see this very construction of spaces and this conjugate spaces having non-proper values, how we can see it? So we can see that if you just multiply it, you can see it. You can write it if there are x minus iota y. So these are the pair of what I say of these things which are contained here. So you can write it as if you want to modulus of x square, sorry, modulus of y square plus iota xy and iota yx. That's fine. Now the point is that if modulus of x can be equivalent to modulus of y square, this means xy is equal to minus yx. It is antisymmetric. But since linear vector spaces or linear inner product vector spaces are symmetric, linear inner vector product spaces are symmetric. That means that xy is equal to. So we can only change the order of xy to yx if it's symmetric. So this means that xy is 0. So from this x minus y, so if you change y to x, you can from this you can say xy is symmetric. And if and again from this xy, it's yx. So again you can say that z square, so it's 0, z square can be written as modulus of x square plus modulus of y square. Or modulus of, so if it is you can say it modulus of x. So now the point is what? The point is if lambda 1 and lambda 2 are the values are the proper values. If lambda 1 and lambda 2 are the proper values, lambda 1 and lambda 2 are the proper values, 1 and lambda 2 are the proper values of u plus, and we have assumed that lambda 1 is not equal to lambda 2, or lambda 1 bar is not equal to lambda 2 bar, a conjugate of it, and z1 is equal to x plus iota y1, and z2 is equal to x plus iota y2, x2 plus y2, or the corresponding proper values of or the corresponding proper vectors x1, x2, y1, y2 in V, then z1 and z2 are orthogonal. Since z2 bar is a vector belonging to, so we have to have an orthogonal construction to begin with. That's why it's the product of these, it came out to be, and this it came out to be 0, because for non-proper values, the product of that condition satisfies there. And this corresponds to those proper values. Then Z1 and Z2, or from this argumentation, you can have Z1 and Z2 as an orthogonal. So if we want to write the same thing in terms of real product space, in terms of some real product space, then what we are going to do is that we can further extend our this exercise to complex inner product space, complex inner product on V plus in terms of real inner product V. So we'll have x1 x2 plus y1 y2 gives, so you can have x1 y2 minus y1 x2, it will be 0. So if the same way x1 x2 minus, these are two pairs of these things, you can have x1 y2 plus y1 x2. So this means x1 and x1 x2 y1 y2 are pairwise orthogonal. So the unitary transformation would also have unitary transformation u plus, it would also have some real proper values. So that's it. Such that u plus x plus iota y is equal to plus. So we have tried to tried to expand the complexification process which have non-proper values to some real thing, something. And then the real part is ux is equal to plus minus x and uy is equal to plus minus 1. And the real proper values of u plus are plus 1 and minus 1. Now we are going to take the final step. The final step is we are going to choose some orthonormal basis. Choose some orthonormal basis. Chi1 in the linear manifold of solutions. So here the book has used the solutions of also in the construction of having a geometrical intuition. So we are maybe constructing this thing in some space, some plane or some plane. So manifold is two-dimensional sort of plane from which we extend these bases. We can construct that finite dimensional vector space in two-dimensional space if it's linear manifold. In linear manifold of solutions, ux is equal to x in V. And if we choose orthonormal basis, say we'll choose orthonormal basis this in the in the linear manifold of solutions. In the linear manifold, so first one we have chosen this because we are pairwise constructing things. First one is this, second one is in the orthonormal basis, it's minus x in V. So the sets, this set and this may be an empty set, maybe empty, maybe. So now next we are going to say what are the complex proper values which we are going to construct. What are the complex proper values, complex proper values lambda and lambda bar of u plus, and to choose the orthonormal basis. In linear manifold of solutions, V plus, and if this is a complex number, if zg is equal to xg plus iota yg, this is one solution. Now, if we are going to follow the book, the exact values he has given to these set. So he uses we follow the book that if we define it this way, and the scalars, the value of the scalars, let chi lambda be a set. So if the values of the scalars are in this root of 2y1, root of 2xr, root of 2yr, so xr, so these are discrete, x1, y1, to xr, so these are pairs x1, y1, x2, y2, so xr, yr of vectors in V. So this implies the union of all sets in this and this one, this and this. This one with this linear manifold, the other with this chi of minus one, which has orthonormal basis. For all proper values of lambda, or u plus, in the orthonormal basis VV. So if chi1 has, so the thing is that if I'll just use it here, so if from this will come here. So if chi1 and this which are orthonormal for all proper values lambda of mu plus, so we obtain an orthonormal basis. Orthonormal basis is V, and if chi1 has, so this is a choice of this example taken from book. If chi has three elements, then chi inverse has 4 elements. Why it has the 4 elements? So 4 elements, and there are 2 conjugate pairs, lambda 1, lambda 2 for 1, sorry, lambda 1 and lambda 1 bar for 1, and lambda 2 and lambda 2 bar for its conjugate value of the other. The matrix 2, so matrix can be constructed like this. If I just see it, it has the first has the 3 elements, 1, 1, 1. The other has the 4th element, minus 1, minus 1, minus 1, minus 1. Then you can have these values alpha 1, minus beta 1, beta 1, alpha 2, alpha 2, alpha 2, the last one has 2 elements, so it's minus beta 2, it's beta 2. So if you see to the matrix has the form, the matrix takes the form, this matrix. If you see to this matrix, or I'll construct it here, that will be better. I'll construct it here. I'll construct it here. Or you can see it, I just see it. That will be. One, 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 minus one, minus one, minus one, minus one, alpha one, beta one, beta one, alpha one, and alpha two minus beta two, and beta 2. You can see to the book, so that if you see it, if you just try to see it in terms of the mean diagonal 1 followed by series of minus 1, there are 2 bucks. The last one, this alpha beta, you can have the form of alpha minus beta. Beta alpha. So you can have the solution can be in the form of alpha square plus beta square is equal to 1. And we can have a trigonometric representation of the same thing. That's the point. So this is a sort of exercise in which we have constructed a space, complex space, and some basis and some orthonormal basis, and their representations, normal space and then complex space. How can then at the end, which have non-proper, not proper values, because it's orthogonal, the net it will be equal to this 0. So a lambda is equal to this. So how we can construct it, and what's the matrix representation of those things? How we can simplify those values, proper values, one. So we can, this is sort of simple way, the way we complexify things. So how we can have a orthogonal transformations from a certain sort of complexifications, where x1 and x2, y1 and y2 are pairwise orthogonal. So this is this. Now the next part of it is so orthogonal functions of those orthogonal transformations. Functions of transformations. Again, the functions of the transformations can be functions of the transformations means that, so usual concept for the third on the is the useful concepts, in the theory of normal transformations on the unitary spaces is that of unitary transformations is that of a function of a transformation. So if A is a normal transformation, its spectral form alpha I Ej, and Ej we have discussed in the previous class. They are projections, orthogonal projections in that sense. So if F is a arbitrary complex value function defined at least by the points alpha g, then we define a linear transformation can be defined as alpha g Ej. Alpha g Ej. So we have polynomials and even for rational functions. So for each, for example, for each complex number lambda, f of lambda is 0 whenever zeta is not equal to lambda, not for proper values, or f of lambda is equal to 1. So it's like either it's orthogonal or it's not. We have two cases. Either it's the value of these is 0, it's not equal to lambda, or it can be 1. And f lambda A can be a perpendicular projection on the subspatial solutions with Ax is equal to lambda x. So if you remember, we observed that f of zeta, this is is equal to 1 by zeta, and f is defined, and f of A is A inverse, and f of zeta is zeta bar F of A. So if it's f of A is f of zeta bar, then if you define things this way, so it implies that for any arbitrary rational function zeta and zeta 1, we obtain zeta goes to this A and zeta bar it goes to A star, and 1 by zeta is A inverse. So now how can we construct, if you remember, the relationship of adjoint and A star is equal to A, or it is equivalent to A inverse. That's a typical property. So if we extend that property to our construction of how we define these projection on that vector space, finite dimensional vector space. So how it will come out to be. So if you consider f of zeta to be root of zeta for zeta greater than equal to 0, which is positively definite, and A is defined as alpha j e j, then root of A can be defined like this. Root of A is y is not, this is the projection. The point to mention is why we are introducing root is basically the square of this root should be an inner product, and it should be also have a property of positive definiteness. It should be positive definite such that if A is equal to B square and B is greater than or equal to 0 and B is equal to root of A, and let B be defined as beta k f k, then sigma. This can be extracted, this property can be just arrived at B square. The complex conjugation of both is A is alpha I, alpha j, e j. So if you define things this way, be defined this way, so you can have the square of this thing. So you can be defined it in terms of this alpha j. So where we started, you can have this construction plan. So what are the applications of what we have extracted? Existence of roots for positive operators, given that we have can. So if we have root A and B as functions of our polynomials of A and B respectively, then modulus this A of B can be written as so A, B, B, or they can also be written as root of A square, root of B square. So we are just trying to and root of A and root of B are self-adjoint and commutative, and therefore their square is positive. So this is the way we can, in the simplest cases, for an orthonormal coordinate system, in the spectral theory, for example, how can characterize a given matrix which has some positive definitivity attached to it, such that this A can be also greater than or equal to 0, and determinant of A is greater or equal to 0. And then if you remember this, how we can construct the proper values out of it, this thing. Now the next part is you can also have polar decomposition. Decomposition. What do you mean by that? Polar decomposition? Polar decomposition means we'll start with the theorem. Start with the theorem. Theorem. Start with the theorem. What does the theorem say? I'll write it. The theorem says that if A is an arbitrary, A is an arbitrary linear transformation, then on a finite dimensional vector space, inner product space, sorry, that will be better. Inner product space. So, and there is a uniquely determined positive transformation P, and there is an isometry U. There is an isometry U such that A is going to be U of P. Then, if A is invertible, U is also determined by A. So if A is an arbitrary linear transformation on a finite inner product space, that's fine. Defined it's a complex vector space. Then there is a uniquely determined positive transformation P. There is a uniquely determined positive transformation P, and there is an asymmetry U. There is an asymmetry U such that A is going to UP, and if A is invertible, U is determined by A. So if A is invertible, this means 1 UP A inverse invertible means this is 1. So U is also determined by A. So U is also determined by A. So this is the point. U is also so which is how we have to show it as a U is uniquely determined by A. So this is a positive. This is a unique constraint that U can be determined by A, provided that A has an invertible property. If A is invertible, then U can be determined by A. So this is what we have to show. So again, what we are going to do, so we are going to not take a general proof, we are going to see that proof works in some specific way and then see how it works here in this case. So since it's positive, positive A, so the point is that we have to show, since if A star A is positive, then what? So we may find its unique positive. So we may find its unique positive square root. So P is equal to A star A. So we can define P in terms of A star A is positive. This means P. So we can have it the invertibility property means if A is invertible, P is uniquely determined by A. If A is invertible, U is uniquely determined by A. So we define P as this A star A. And if A star A is positive, then there is a unique positive square root such that V is equal to PA inverse or VA is equal to P. So this is what I am saying. VA is equal to P. VA. If A is here. It's a invertible. It's VA is going to P, nothing fine. That's fine. V, it's A inverse here. So sorry, it's not this thing. So it will be A inverse here. Then only this is the thing. Then P is going to be fine. Then P is going to be. So this means so V star this means V star inverse is P, or this means that V star V is equal to PPA inverse. So V star V is equal to A star A. Now again, so VA is equal to P, VA is equal to P, VA is equal to P, so V star is equal to A star, so that's fine. So we can write it VA is equal to A star inverse twice. So this is this conjugate of this product of this conjugate V star and multiplied by this. We can write it like this. Or now we can somehow classify them. We can just so A star inverse and this A star A. So again we write P in terms of A star. So one of the P's. So we'll star write it in terms of A star A and A inverse. Yes. That's so. It's all equivalent to one. So that V is an isometry. So that V is an isometry, and we are done. So to prove the uniqueness, we say UP is equal to U naught P naught, and PU star is equal to P naught U naught. So again, to prove the uniqueness, we'll have multiplied by P star, that will be P square. So U star, it will be P U star U P. It will be further written as U naught P naught or P naught square. So this shows the uniqueness in that sense. So that P star, if you assume that A, if we assume that A is invertible, then P square is equal to A star A. And Px, modulus of Px, can be written if we want to write it in terms of these as an ordered pair of these things. So we can have linearity property here. We can write it like this. X, or if you want to write it in terms of P, in terms of A, we'll write it as A star A, X of X, or modulus of Ex. Okay. Again, the theorem 2 says that if A is equal to UP, I will not write it, so if A is equal to UP, I will only state it, is a polar decomposition. Is a polar decomposition of linear transformation A. Is a polar decomposition of linear transformation then necessary and sufficient condition that A is normal is that PU is equal to UP. So this means this is that's fine. So you have to prove it. It's the proof is simple. The two-line proof that is so you can just do it. It's not that done. Now there are one or two properties. One of the property is of commutativity, which is the commutativity as a property. Sometimes it has been shown to hold in linear transformations in general, and sometimes it doesn't hold. Or linearity conditions holds or not. That's more seen in case of when we have commutativity as a property in the finite dimensional vector spaces. And now, since we are interested in the spectral, basically we are trying to see spectral theorem and its for adjoint and normal operators and the functional calculus which is associated with it, which is a deeper subject. But here, what we are going to see for a theorem, a theorem which will just specify things more, is that the theorem says that two self-adjoint representation, two self-adjoint transformations A and B on a finite dimensional vector space, on a finite dimension inner product space are commutative if and only if there exists, a self-adjoint transformation, a self-adjoint transformation C, and there exist two real valued functions f and g on a real variable such that a is equal to f of c and b is equal to g of c. If a c exists, like previously we also said, a b is equal to c, if you remember. If c exists, then we can choose c as h of a into b, where h is the suitably function of two real valued variables. So if two self-adjoint transformation, we have two A and B are two self-adjoint on a finite dimensional product space, that's fine. And if they are commutative, also we have to show the commutativity as a condition is strictly exercised or strictly obeyed. So for commutativity hold, if there exists an adjoint transformation C, for commutativity to hold, there should exist an adjoint transformation C such that C can be expressed as h of A into B, where h is, there are two real value values. So commutativity should hold for this. So how can you show the commutativity? Commutativity is a property, has to be obeyed. So the sufficient condition is similar to what sufficient condition is similar. The sufficiency condition is clear, we prove only the necessary condition. So we have A is equal to alpha I ei, B is beta j fg, be the spectral forms of A and B, and if A and B commute, and it follows from then E and EI and FI also commute. Okay? Also commute. So if A is defined as this, B as this. So if A and B commute, then these elements, this and this should also commute. That's fine. So let h be any function of two variables. Such that h alpha I beta g is equal to gamma times ig. So if we want to define h in terms of these alpha I beta g in terms of two real value functions, then c of h a or b can be defined. Now we have translated these variables in terms of this I g h of alpha I times beta g ei and fg. Fine. So we have done this. It's clear that h may be chosen as any, and the same is true for f and g. Well, now if we have f of gamma ig as alpha I and g of gamma g as beta g for all I and j, then from this we can see f of c is a, g of c is b, so everything is proved. How? So we have shown that f of gamma ij can be as alpha I, find g of gamma ij is beta g. So you can have alpha I is written like this. So beta I, that's fine, is written as this beta g is written. So we have written these two elements in terms of the a and b in terms of this. So we have written h as we have expressed it as a function of two real variables, alpha and beta, where alpha I and beta g can be further represented by this and this function. So this is in a simple way we have shown. So the theorem 2 says that if A is a, and the theorem 2 is equally not that complicated, it's also easy. If A is a normal transformation on a finite dimensional unitary space, B is an arbitrary transformation that commutes with A, then B commutes. So if A is a transformation which commutes with B, if A is a normal transformation on a finite dimensional unitary space, and B is an arbitrary transformation that commutes with A, B commutes with A. So what he is saying that B should also commute with A star. If B commutes with A, B should also commute with the complex conjugate. So the proof is again very simple. Proof is that we define A in terms of alpha I, ei, be a spectral form of A, then A star can be defined as again. So it will be complex conjugate of this. Is that with the complex value. So f of alpha I is equal to alpha I star, and A star is f of A. Again from this we can see it. So if A commutes with B, it should also commute. B commutes with A, it should also commute with A star. Since A is equal to A and A star are same, they are self-adjoint. So you can see the proof is very simple. Now the constraint comes in the next section. We have self-adjoint transformations of the rank 1. So for the simplest case, it is true. So for self-adjoint transformations of rank 1, things become more so which is positive definite. So the theorem which becomes a bit more subtler in the sense that to rank of 1. So the proper values the matrix will be equal to 0. So but if it's rank 1, it's not necessarily it will be 0, or it will be the adjoint The self A is self-adjoint to positive, then the summands also should take the self-adjoint and or positive value. So if I write a theorem that if A has rank 1 and is self-adjoint or positive, then in every orthonormal transformation, orthonormal coordinate system, matrix alpha ij of A is given by alpha ij beta I beta j with real k such that alpha ij So conversely, if A has this form in some orthonormal coordinate system, then A has rank 1. If converse of it is, if A is this form in some orthonormal coordinate system, the A has rank 1. A has rank 1. And the self-adjoint is positive. So we have, I was just stating the not, I was stating the converse of it, but you have to prove the converse of it. If it is rank 1, then form it should have this form, and the conditionality of rank 1 or being positive is that the matrix, they are the orthonormal coordinate systems. If it's defined this way, it should have rank 1. So the proof again is not that complicated, in the sense that the only thing is that, so if I just, if so if the matrix, we know the matrix alpha ij of the transformation of rank E of transformation of rank E of rank 1 in any orthonormal system is given by and if A is self-adjoint, we must have alpha ij is equal to alpha bar ji, beta I gamma j is equal to beta j gamma I, and if beta I is equal to 0, gamma I is not equal to 0, if gamma I, so if it has rank 1, maybe that's it. The proper values will not be 0. So gamma is not necessarily equivalent to 0. It's not equivalent to 0, then beta j, so if you define beta j, this, you can define it in terms of this and this, beta j, but here if you complexify it simultaneously, beta j can be written as beta I gamma j gamma I 0 for all j once A is 0. Since beta I is, so it's 0 if it is not 0. If it is 0, then it's 0. But if it is not 0, then since beta I is not 0 and gamma I is 0 is impossible. So that's an impossibility constraint is there. So from this we can say beta j can be written as beta I by gamma I bar gamma j is k gamma I. So we have written gamma I in this by double k. For some non-zero constant, k independent of j. So now since the diagonal elements are alpha. So diagonal elements of that matrices. So if it's and so if the diagonal elements may not necessarily be zero in that sense. So the diagonal elements which uh, can be defined in terms of these xj and xi, and further in terms of beta g, gamma g of self-adjoint matrices are real, we can conclude that alpha ig is equal to k times beta I beta g with real key. So we have to show that they are positive self-definite also. The matrix is the value of it can be greater than or equal to greater or equivalent to 0. So what we are going to do? So we have to show the necessary the conditions in that sense. In case so we write lambda in terms of that scalar, we can write it k beta I beta g bar is equal to lambda beta I lambda beta g bar, and shows that alpha ig is equal to gamma I gamma g bar. So for self-adjoint conditions, you can say these two matrices are defined this way. So it's easy to see that. So A elements adjoint transform self-adjoint transformations can be written as sigma I sigma j alpha ij zeta I zeta j. One of them is adjoint. So if you write alpha ij in terms of gamma I gamma j, sigma I sigma j, gamma I gamma j, zeta I zeta j, one of them is complex conjugate. Again, I gamma I zeta I bar, this is one. The second is gamma I zeta I. This is zeta I, this is zeta bar, it's complex conjugate of this, it will be square of this, modulus will be square of zeta I bar square, which can be greater than 0. So as a consequence of this theorem, it's easy to do remarkable theorem on the positive matrices. So you can show that if a rank 1, if it's self-adjoint and positive definite, then every orthonormal coordinate system of ij of A given by, so it's given by this, rank is this, alpha ig is in terms of gamma ig, gamma I, gamma j, two matrices. One matrices, we have written it in terms of gamma I and gamma g bar. Where I corresponds to this, G corresponds to this complex conjugate. So we can show it's positive definite in that sense. The other theorem is, which I'll only state and then we'll stop. The other theorem is that if A and B are positive linear transformations whose matrices in some orthonormal coordinate system, alpha I, j, and beta I, j respectively, then the linear transformation C whose matrix gamma ij. So we have again defined two matrices, alpha ij and beta ij, in terms of some other matrices Cij, C with the elements gamma ij in the same coordinate system. Then gamma ij can be written as so. So it's again the way we have done the previous theorem. So elements of gamma or C can be written by its A and B. Gamma can be written in terms of C can be written in terms of A and B. C is a combined matrix. These are the individual elements. It can be written like this. And I and G should be positive. So again, we'll simply write it. The way we did the one of the proofs here. We'll write alpha ij is equal to alpha ip. The corresponding is alpha jp bar. And this complex conjugate of it. Beta ij we'll write as beta qi, and the second as a complex conjugate of it, qi bar. So now we have alpha I, and these two are the products as products. So the product of this and this will be equal to gamma ij can be written alpha ij bar, beta ij bar. you write these two products here. So it will be alpha I P beta Q I alpha J P bar and beta Q bar I. So this is it. So again, so these are, so this is complex conjugate of it, and the thing is that I have written it in this form. The proof shows that is self-adjoint. This is also called in literature as gamma Ig. This is also called in literature Hadamard product. Hadamard product. So how we define a Hadamard product of alpha Ig and beta Ig. So how we can write these self-adjoint matrices in terms of some single matrices. So that's known as maybe he is the mathematician, his name. So we'll stop here.